So I'd say welcome everybody to MEE Live. This is a series of YouTube things that we do related to papers that have either just about to come out or have come out in methods in ecology and evolution. So if you are a person who is writing a paper at the moment, or you've just published one and you're interested in doing one of these, do reach out because we're always really keen to do them. They're always great fun and people do watch them afterwards. We will put a video of this up as well on our YouTube channel, so if you do want to watch it again at some point. So I'm just going to post the British Ecological Society Code of Conduct, which of course we'll be using in the same ways we use it for any meetings. If you have any issues, do just click on that link and it'll give you some ideas of who to contact if you've got any problems, or just message me in the chat if there's an issue. I'll also repost a few times as we're going Quinn's link to the materials for this workshop, because I know if you've only just joined the chat, you won't have seen those links. So I'll just keep reposting that. In terms of questions for this, if you have any questions, we'll do questions at the end. But if you are thinking of something and you want to start typing a question, feel free to type it. Quinn will just keep going and I'll keep track of those questions and ask them at the end. Or if you'd rather speak, you can, when we get to the question stage, if you can unmute yourself and just put your hand up or something, and then we can do questions that way as well. Or you can continue typing them in the bottom. So I think that's all the information I need to give you. So without further ado, I'm going to hand over to Quinn. Thank you very much.
All right, thank you. I'm going to put a share screen on. Hopefully everyone can see that. Is that all good?
Yep,
Uh,
perfect.
Great. All right. So, welcome everybody. Today I'm going to be demonstrating the functionality of this new method we developed for fitting community time series that we developed here at UW-Madison, and we turned it into a R package called multinomialTS. And I'm going to demonstrate how it works using two case studies, and it'll be followed by a short coding demo. Both case studies are actually paleo examples, but the model will work on any type of community count data. I just use paleo examples because that's what we really aimed the model at developing it for and tested it on, and sort of the realm of expertise of Jack Williams and myself. Change slide. I already said that. So, of course, there are plenty of people behind this effort. Most importantly, there is Tony Ives, who is the mathematician behind the model, and Jack Williams, who is the paleoecological expert, and many others who contributed expertise and data along the way, most of which you're going to see in this talk and coding demo. So the aim of this R package and the state space modeling approach is to be able to try and start to disentangle the relative effects of abiotic drivers and biotic interactions in ecosystems. So how strongly is the environment influencing the species in the system, and how are the species or taxa within the system interacting with each other? And we want to lend some statistical support about hypotheses around the drivers of community change. Additionally, we wanted to tackle this issue that we have quite regularly in many data sources, but particularly paleo data sources, of unevenly spaced samples through time. Most time series analyses have a fundamental assumption of having nice even sampling through time. And additionally, we have this issue of count data or multinomially distributed data where all the data, we don't have absolute abundances of any given species or taxa, we have the relative abundances. So just very briefly on the multinomial distribution, just to clarify, what we're looking at is the counts of n individuals across k categories. So typically, like as opposed to the binomial distribution, which is typically described as successive trials of tossing a coin, where there are only two possible outcomes, say the presence absence of a species. This is more like rolling a die multiple time, where you might have multiple outcomes. And the issue of what relative abundance comes in with this because everything always is going to sum to n. So that is to say, if species A is 10% of your data and species B is 50% of your data, then the remaining 40% of your data must belong to species C, for example. So we can only generate estimates for K minus one taxa in the system. And so, one way you can estimate with this model, and the point of using it is to go beyond descriptive approaches to, say, using cluster analyses on ecosystem species compositions, and generate actual coefficients for autoregressive processes, interspecific interactions, driver-taxa relationships, and combinations thereof. I'm actually going to talk more about the application of the model rather than delve into the math, but I'm going to put this slide up here. This is really Tony Ives' realm of expertise in developing the maths behind the model. But just in brief, state space modeling attempts to predict the true, in inverted commas, the true state of the ecosystem from the observable variables about that ecosystem. And those observable variables are usually a matrix of our species, so our site by species matrix through time, alongside a bunch of environmental covariates. So maybe we have measures of temperature or precipitation, for example. And it does so using two equations. It splits into a process equation that models the ecological processes of the system, or describes the ecological factors driving change, and a second equation that is the observation equation that describes how data are sampled. So it very neatly split sources of uncertainty into process and observational error. The main thing you need to know and take away from those first two slides, though, is that the package models the multinomial distribution or count data directly. It accepts multiple covariates of mixed types, so multiple driving variables. And we can generate estimates for taxa interactions and driver taxa relationships. Of course, this is a challenging process that we're trying to tackle here. So there are a few decisions that have to be made along the way. And so when we're looking at the fitting process, we're gonna look at this more in depth following the two case studies, but we've got to make some decisions along the way. We got to figure out what taxa we are most interested in estimating interactions for. And we got to figure out what our reference group is going to be. So for that reason that we can't generate estimates for more than the K minus one taxa, we need this sort of out group that the estimates are generated relative to. We've got to choose a window span or prediction resolution. So we're going to bin our data. Um, and the best way to think about that is what is a reasonable prediction resolution that we can estimate ecological change over. I'll go into more detail on that in a second. And then we've got to make some decisions about how we're going to fit the model. And we're going to set up some multiple hypotheses, and we're going to fit the model to those hypotheses or components of them. And the following two case studies are going to follow the same arc of setting up hypotheses, choosing focal taxa, and fitting the model. So we got these two case studies that we've applied the model to recently, both of which are currently in review. So we have this Lake Tulane in Florida, which is this long 60,000 year long record. It has multiple covariates. It has fungal spores as a proxy for megaherbivory in the past. CO2 and delta 18 oxygen isotopes as climate proxies, Heinrich events, and charcoal accumulation rates as a proxy for fire. It's quite a well-studied system. There have been multiple publications on this lake over the years. And our second case study is Sunfish Pond, which is the one that we use in the paper. It's in Pennsylvania and also in the US. It's roughly a Holocene length record, a little bit more, 13,800 years. In this example, we got just the one covariate, which is lake level for hydroclimate. The full analysis that is in review has additional covariates, but this is a reduced example that we used for demonstration in the paper and for today. So jumping right into Tulane, the Lake Tulane case study. So for anyone who's a little less familiar with looking at the paleo examples of pollen diagrams, here what we have on the left-hand side is on the y-axis, we have time going from the present up at the top of the graph to the past down at the bottom. Each panel is a species or a functional group. So we have oak, pine, herbs, grass, and our reference group, which is other. So in this case, we have a good amount of literature to base our groupings on. So we have these two functional groups, grasses and herbs. So we have selected all the species that fall under those groups and clumped them into grasses and herbs. This is just based on literature, previous literature. And Lake Tulane, or the surrounding environment, is really a story of pine and oak. These two species massively dominate the system over the last 60,000 years. And so we really want to target those two taxa for our estimates. And on the right-hand side here, we have how the covariates change over time. So we have our charcoal accumulation rates, our oxygen isotope, CO2. Heinrich events we included as a binary variable. So this is basically on, off. Is it happening? Is it not happening? The reason for that is we don't have great estimates for magnitude. I know there's literature on that, but we simplified and went for using it as a binary variable. And then we have our fungal spores as our proxy for megaherbivory. So we've got lots of questions we could ask about this data set. And I'm going to show results just for the one test because otherwise it becomes an overwhelming number of results. And this is really a demonstration. So the things we did want to ask are questions around are biotic interactions or climatic variability the primary drivers of these pine oak dynamics that we see in the pollen record? Is megaherbivory a significant driver of vegetation change, and is fire a significant driver of vegetation change? And so the parameter selection we use a prediction resolution of 200 years. I'm going to go back and detail that for you in a second. We picked the two functional groups, herbs and grasses, and we picked our two key dominant taxa. And in this example, I'm going to show you estimates for the interactions, for the model that included interactions between pine and oak. So I'm going to go back here just to clarify what I mean by the prediction resolution and why we need to bin our data. So in essence, the model is going to make a prediction at every time step. And so if those time steps were annual, we would be attempting to make predictions, 60,000 predictions from, say, 100 or so observations in the data. I forget exactly how many observations we have in this full record, but that as an abstraction, we can't realistically say we can estimate annual ecological processes over 60,000 years from a couple of hundred observations. But we can realistically, also the model would take about 200 years to run, but we can realistically make predictions of ecological processes over, say, the century level or 200 years. So that's why we bin the data into a sort of more manageable prediction resolution. This case study, the other reason I like to use it, is because all of these covariates have different temporal resolutions of sampling. So that gives us a bit of a challenge. In the state space model, it can handle and is designed to handle gaps in your state variables, or in this case, the pollen matrix. But it needs a complete set of covariates to make those predictions at every empty or every gap in the pollen data. And so to deal with this, where there are small gaps, what I would do is I would just model out those small gaps. So I'd fit a GAM, for example, or maybe if there's a really small gap, just simple linear interpolation. So if there's a little gap in fungal spores or CO2 or something of one or two time steps, it's perfectly acceptable to fill in those time steps with modeled value. I would definitely caution against using really sparse data in your covariates and like over smoothing a peak, like a peaky signal with a GAM, for example, because then you're changing your input signal. But filling in those small gaps, I don't have any issue with that. And these are the types of results that we output from the model. So in this case, on the right-hand side, each panel is a covariate. So we have Heinrich events and charcoal accumulation rates, etc. And each, on the y-axis, we have ticks for each species. So what we're looking at here, for example, is the effect of Heinrich events on each species. And we've got a strong effect of those events on pine, which is something we sort of expect to see from previous literature. So it's a bit of a comfort that we're seeing something that agrees with what we know from the literature. Um, we're seeing some climatic effects on oak and pine. And then on the right-hand side here, we have the interaction effect. So we estimated the effect of pine on oak and oak on pine. So we got rather large error bars here, so they're not coming out as significant. Um, statistically, but we don't put that much stock, of course, in p-values for hypothesis testing. There's lots of literature on why not to do that. But also during simulation or the simulation testing that we were doing to validate this model or assess the performance of the model, we found point estimates to be very good a lot of the time. So oftentimes, this estimated coefficient was so close to the simulated input value that we're recovering the true value pretty well anyway, regardless of the error bars. And of course, we expect wide error bars in something like paleo data, where the data are just so sparsely spread over time. From this model fit alone, this would indicate that, for example, climate or Heinrich variables and Heinrich events and climate-related variables have a stronger influence than the pine-oak interactions as far as the patterns we see and the ecosystem dynamics. But in reality, of course, well, I'm just showing you one model fit here. And the idea is that we fit the model in multiple ways. So we have, for example, our null model with no interactions. We have our full model with all the interactions. We have pairwise models. So we have to build up the picture from multiple model fits. The idea behind this study was to show that we have to make those decisions around the data, interpolating small gaps in our covariates, choosing our prediction resolution, choosing focal taxa, functional groups, and then fit a model or fit, in this case, I showed the example of one model to part of one of the hypotheses we wanted to test. And then we repeat that process, we get multiple results, and we can rank our models and build up a fuller picture. But I will move on to the second case study, which is one we use in the paper, which is a much shorter record. It's Sunfish Pond in Pennsylvania. And in contrast to Lake Tulane, instead of being able to group into functional types and then have these two incredibly dominant taxa in the ecosystem, we actually have five dominant taxa, which show very strong dynamics of ecosystem change. So we want to model each one. We don't want to group those taxa. We want to keep them separate and individual. And so we picked out the most important taxa from the system, and then we grouped all the less abundant taxa into this other reference group against which the estimates will be made. And also in this example, we have lake elevation, our proxy for local hydroclimate, as our environmental covariate. So the questions that we wanted to ask are similar. Are climatic conditions a stronger driver of change in taxa interactions? In the analysis that's in review, we have additional covariates that are like regional drivers of climate. So we have that additional hypothesis are local conditions a stronger driver or regional conditions a stronger driver of ecosystem dynamics along with taxa interactions. So we have a nice little triangle of potential hypotheses and multiple models we can fit to the data. Because this is a shorter record and has quite a nice tight sampling of pollen resolution, we could choose a window span of 100 years. Could actually fit it a little bit finer than that as well, but 100 years worked well. We chose the five most dominant taxa on in the system. And these are eastern white pine, hemlock, beech, oak, and birch. And in the example I'm going to show you, we actually use a three-way interaction model. So we tried pine against oak, pine against birch, and oak against pine, sorry, beech, oak against pine, and beech against pine. So in this example, same as before, on the left-hand side, we have the effect of the local hydroclimate on each species. It's showing quite a strong positive effect on hemlock, which is consistent with what we expect of the ecology of hemlock today, which likes wetter conditions. We're also seeing an effect of wetter conditions on pine. I wasn't too sure about this myself initially, but talking to the main author of the paper, he's managed to get it down to the down to Pinus strobus. So, and he expects that that is a species of pine that enjoys wetter conditions more than other species of pine, which might be negatively affected by local hydroclimate. That's really the main author's area of expertise coming in there, not my own. I'm not a pine expert by any stretch. And then we have our interaction coefficients, which showing that pine is having quite a strong negative effect on beech, but that pine and oak tend to be positively related to each other, so they tend to co-occur. And the important thing to remember here is that this is quite a complex story that we're trying to fit, and we're only looking at the one model fit here. So in reality, how I broke this situation up is I did full pairwise interactions. So I don't know how many model fits, many model fits to estimate all potential interactions across species. And the reason for that is we can't reasonably generate estimates for all five species simultaneously in the system when we only have, I think it's like 140 observations over that time period, because that means the number of estimates we're trying to fit, or the number of coefficients we're trying to estimate, sorry, becomes so large, and based on so few observations, we're going to get gibberish out the other end. We might be able to do that if we had an incredibly strong time series of data of our input data. But in this case, in order to deal with those with that issue, we can break the problem up into smaller parts and fit multiple hypotheses or different components and begin to build up that picture. Um, So this case study is really aimed at looking at those model decisions. So as opposed to Tulane, where we looked at how we deal with covariates and filling in small gaps in covariates, but it has a fairly stark story in its pine oak dynamics. Sunfish Pond is kind of the opposite in the fact that it's got very strong dynamics across a range of species. But we've got to make a lot of modeling decisions about how we can tease apart that story. And the ultimate analyses that is in review right now will do that. It will have multiple model fits, it'll have additional covariates, and so the story we begin to see will become a little bit stronger than this one example. But at least what we can see here is that we are beginning to pick up some interactions and effects of local hydroclimate that are consistent with what we would expect to see based on contemporary data. So, sort of compared the case studies along the way as it is, but I'll give a quick summary of the two. So Lake Tulane had this long record, multiple covariates, few dominant taxa, some really key driving relationships and kind of obvious questions we might want to ask about climate versus species interactions. We're likely to lose fine scale processes, for example, post-fire recovery, because we got that large 200-year prediction resolution, that binning window of 200 years. So anything that happens at a sub 200-year scale that might happen over, say, decades is likely to be not picked out in statistically. Sunfish Pond is a shorter record, and we use a single covariate, but we had multiple taxa. We have a finer resolution of our sampling, or temporal resolution of our pollen data, I should say. But we're possibly missing some explanatory power from unmeasured variables that might be driving the system, which is why the full analyses includes additional covariates. Um, So in practice, I only showed testing sort of one hypothesis component, and the full analysis from each site, as I mentioned, you fit multiple models to get different angles. So that's all for me on the case study side of things. Went through that faster than I expected, but I do usually talk faster when I'm on my morning caffeine. I could potentially take some questions now about the presentation part, or I can move directly into the coding demonstration side of things.
Given nobody's actually typed in any questions, maybe if you carry on with the coding, and if anybody did have any questions, if you start typing those now, then when Quinn's finished the coding section, we'll be ready to crack on with questions.
Sure thing. I'm gonna just rearrange some screens. So I see Natalie has dropped in the chat this link here that goes to the slides and the coding demo. So this coding demo is going to have to be very, very condensed. I'm only going to be able to give you a sort of conceptual overview of the code and leave the programmatic details behind. Otherwise, that would need to be a full workshop. This link, this coding demo over here, is the full rendered version of what we're going to see. When I'm presenting it, I'll be presenting it in code format, but it is this very same content just rendered. But if you're interested in using this approach, then there's a much more detailed, full walkthrough here that goes into choosing your state variables, the decision-making processes. It's going to follow the same case study, which is a third case study actually, which is using Story Lake in Indiana. It'll go through also how to download and wrangle the data directly using the Neotoma database API. So it's far more extensive than what I'm going to be able to demo today. But and it's under construction and updating all the time. But I encourage you to go there should you be interested. Um, okay, why do we not suggest? I see a question in the chat. I can answer that now. Why do we suggest not using p-values? P-values are there's two reasons actually. What I could say, I'll mention it in the coding demo. P-values are usually, because of their arbitrary thresholds, let's say 0.05, they're not very useful for binary as a method of like binary hypothesis testing because you inevitably, and this did come up while I was doing some of the real analyses, you inevitably end up with something that's right on that boundary of it 0.051, and so it doesn't appear as statistically a significant at a random threshold. So what's far more valuable when you're interpreting results is to view the results in the context of ecological knowledge about the system, and you can get the coefficient estimates. As I mentioned, they tend to be. I found that they recovered point values very well. So maybe the error bars were just slightly too big to come out as statistically significant in the test. But ultimately, that doesn't sort of whether the p-value is red or not doesn't really mean too much. And if you're interested in reading more, because there's quite a lot of literature on it, I usually take the approach of setting up the multiple hypotheses and then ranking all the model fits, and then you don't throw out anything because you say, well, it wasn't statistically significant because, well, it actually, it might have been statistically significant if I had 10 more data points, 10 more observations to narrow those error bars. It becomes too arbitrary. Um, and then I see a second question, do ecological response variables need to be taxa, proxies? Um, or would this work, for example, community-weighted trait means ranges? Range. Oh, that's a good question. Um,
Should we just read that out in case people can't? Sorry, I didn't
yes. So the
realize you
question is,
were question. I thought you were still doing code. Okay, so Jacqueline has a question which is wondering about inputs. So do your ecological response variables need to be taxa or proxies? Would this work with, for example, community-weighted trait means or richness or range filling or other metrics of biodiversity or ecological responses?
that is a good question. It's a hard one to answer. So they don't have to be taxa. It will work with any form of count data. Trait means, though, that wouldn't come through as count data. I'm trying to think if you might be able to either transform it into the right space for the model to work, or I'm not going to be able to give you a great answer for this right off the top of my head. I'll have to think this one through a little bit. I've only ever used it directly on count data that have the multinomial distribution, but then ultimately the model will take in any number that it used. So I'm wondering if you can transform it to an appropriate space that will work with that multinomial distribution. I might have to get back to you on that one, Jacqueline. I do know who you are, so I can probably have a check through some of my math and see if I could make it work on something that
So I think that
forces.
was nicely clarified in that ideally it's meant to be count data, right? That's what you're mainly.
Ideally, yes,
Yeah.
yes.
So yeah, I think that's a good clarification to have. Um,
Um,
did you have any more code stuff you wanted to
I
show?
do, yes. This we're going to go through a quick coding demo, keeping an eye on the time. I'm going to keep this fairly concise. So this is just going to be an overview of the programmatic side of fitting the model. And the data for the story lake are built into the package, so we can read them indirectly. Uh, if you've got the package installed, the data exist. And I'm going to zoom in one, actually. I hope that's a little bit better. So what you're seeing here, I'm actually using VS Code rather than RStudio, but what you're seeing here is my code on the left and the R console on the right, the interactive R console. So you might be more familiar with seeing that in like RStudio, but it's going to work the same as um, running R in any IDE. So we got some data loaded up. We can check out what the data look like. So in this case, the data, what I begin with, I keep the two matrices, the predictor variables, which is going to include our charcoal accumulation rate. So we just got the one covariate here. And we've got our pollen data. So our response variable as a separate data frame. And I'm going to keep age and depth involved because those I'm going to use as a joining variable. This is actually not the data that the model is going to want. Ultimately, the model is going to be, because it's a mathematical model, it wants matrices, so it's just going to get a matrix of data. But we've got to do our choosing our focal taxa and choosing our prediction resolution first. So we can have a look at the data. Helps if I source the packages, doesn't it? So we got this really wonderful data set on Surrey Lake. It's about 8,000 years long record. The covariate charcoal is sampled at every centimeter, so we've got this wonderful fine resolution charcoal data set. And based on the paper that this written about this data set, which is by Nora Schlenker, it's cited in the HTML document. We know that hardwoods are important functional groups. So based on the paper, I grouped hardwood taxa, and then I tried to estimate coefficients for elm, beech, and oak. As you can see, oak is incredibly dominant in the system. I should say I'm plotting, same for the talks, I'm plotting everything as raw counts, which may annoy some paleoecologists who like to see things in relative abundances. But seeing as I'm modeling raw counts, I also have a tendency to plot raw counts. Up at the top of the data set here, we see this massive rise in the other reference group. Ideally, this isn't ideal, actually. We want our reference group to be relatively stable. So I was tempted to just cut out those three observations up there. This is from like European settlement of the Americas, where we see this massive spike, and I think it's ambrosia, a big spike in charcoal. But it gives us quite a nice visual example of what happens, so I left it in there. Um, and so we got to choose our prediction resolution. So how are we going to bin the data? And usually I do this by just checking out the differences in successive ages. So we have our age depth model, and I'll say have a look at the maximum age divided by the number of observations. So we have sort of like 80, well, not surprisingly, that's very similar to the mean age difference. So it's roughly 85 years difference per sample. And then I'll check out the range of that age difference. Let me get that closer to the center of the screen. So our smallest age difference is 11, largest age difference is about 220 years. And this is how I'll start to get a picture of what is a good resolution. I'll also just, there aren't that many samples over the 8,000 year long record, so I can eyeball them directly. I'm like, okay, most of those are well within 50. There's a couple at 100. There are clearly not many extreme values. I could make a histogram of this. It's just some exploration to see, okay, what would be a good prediction resolution? And what makes for a good prediction resolution is you want as many observations of your state variables, in this case the pollen, you want as many of those to fall within as few observations to fall in a single bin as possible. So ideally, each observation gets its own bin. What we want to avoid are bins that are so wide that we start to clump our observations of pollen. This may be unavailable. You may have to clump some observations of pollen, but ideally each observation will end up in its separate bin. So that's what I aim for. So judging by this, I had a look and I was like, okay, I can have a bin width of 50 years. I would have experimented with, say, maybe probably 25 years, 75 years, 100 years. I did some sensitivity analyses on the effect of the bin width, and it is surprisingly low. Actually, I expected more effect. So whether it's 50 years or 75 years really doesn't make much difference. And then what we want to do, I forgot that I'm going to now join up my data. So in this data frame, we now have our state variables, our pollen, alongside our charcoal accumulation rate, our predictor variable, and our ages and our depths. And I join those all together because I'm now going to bin the data, and I like to do this once with everything joined up. So as you can see, charcoal, since it was sampled at every centimeter and has more observations, we're going to have like one pollen observation, loads of charcoal observations, one pollen observation, loads of charcoal observations. This is good. This is great. This is what we want for the model. We want a complete set of covariates, and we can handle those gaps in the pollen. And so now we're going to bin our data, and of course we're in those 50-year bins. And what we can see here is the binned output. So now instead of these huge long gaps, which are every centimeter in the core, we just have bins. We have bin at 160, 159 bin has no pollen, but it has charcoal, and so on. We have I can't speak. Here we have charcoal and pollen. Here we have charcoal and no pollen. Great. This is how we want things to look. It's important to remember that the model runs from the past to the present. So it's important that your oldest date is up at the top. From that, now that we've binned the data, as I mentioned before, the model is going to want just raw matrices, and it doesn't want our time bins or our age as accidentally included as predictor variables. So I'm just going to split out into two matrices, one matrix of pollen, one matrix of covariates. This would be multiple columns if I had more covariates. All the zero data are replaced with NAs just to ensure that there are no accidental zero counts. The model will skip NAs. And we've got to go through this process. We've got to do a two-step process. We've got to find some initial conditions to begin the state space model with. And how we do that is we fit an initial model, which is a GLMM. So it's a multinomial GLM. I'm not going to be able to explain what all this code is doing sort of line by line, but I'm just going to tell you what I'm doing along the way. So I'm finding an index of where all my pollen observations are. So we have an observation at row 1, nothing. We have row 2, nothing, nothing. So that is what this index is implying. This is just the rows at which there are pollen observations. Then we've got to set up some matrices for the GLMM. And remember here, we're just trying to get a starting point for the main model. State space models have a bit of a paradox. You predict time step 1, 2, 3, 4, 5, 6, all from the previous time step, but then you end up with the inevitable question of what happened at time step 0. So we need something to fill that gap with that is a reasonable estimate, and we get that reasonable estimate by fitting a model to the data, a separate model. So here we're setting up some matrices that the model requires. The B matrix is a matrix of the effect of the environmental drivers on the covariate, on each species. So we have 5 species, and we're going to have 5 columns, one for each species. We're going to have 2 rows, because the first row is going to be the intercept of the model, and the second row is going to be the effect of charcoal accumulation rate on each species. So we're literally just setting up matrices that will be filled. We set the first column to 0, because remember, we're not estimating values for our outgroup. And everything that is set to NA is what the model will fill with an estimate. It's like a placeholder. So these will eventually be values. So this is just some structural requirements of the model. We can then fit our GLMM. And the GLMM, what it doesn't do is it doesn't handle gaps in the data like the state space model, and it doesn't generate estimates for species interactions. But it'll give us a starting value for our B matrix, the effect of driving variables, and our cross-correlated error matrix, which is V. This is all explained much more in-depth in the tutorial. So, like I said, I'm going to give a quick demo, given that I've got about 10 minutes remaining. So once we fit that model, we get an output that is probably something that you're more familiar with seeing from fitting GLMs or LMs to data. And we get a bunch of coefficients. We get our intercepts per species, and we get our effect of charcoal accumulation rates on each species. I should go back into the programming and put names here, but they're in order. So here we have other, what are hardwood, elm, beech, oak, other hardwood, elm, beech, oak, their intercepts, the effect of the environmental driver on each species, and our V matrix. So what we've done here is we fit a model, and we're going to use the output of that model as our starting conditions. We're not too worried about how accurate these are. We just need something that is good enough that the state space model gets a reasonable starting point. And then we set up the state space model. So, like I mentioned, we're going to lift all of these variables from the output of the GLMM. So, B0 is our intercept. It's the first row of the output of the GLMM B. So there we go. That is going to be that. We're now setting up parameters for our state space model. We're going to use the output values from the GLMM as our input values for our starting values as the estimate for the environmental covariance effect on species. And all the rest of this code is doing that same thing. It is just taking outputs from the GLMM and using them as inputs for the structure of the state space model. Where it becomes different is the state space model now has species interactions. So this is where we choose which interactions we're going to estimate. And so this matrix, this C matrix, is the interaction matrix, and it's a species by species matrix. So we have 5 species, so it's a 5 by 5 matrix. So 1, 1 is other against other, 2, 2 is hardwood against hardwood, and we always have an estimate for this autoregressive process, which is on the diagonal. So each species against itself. And then if we want to estimate a interaction, for example, here, I included the interactions for, what do we have? Fagus and Quercus. So I included the interactions of beech on oak and oak on beech. And these are the off-diagonal elements here. Looks a little bit scary, but it is all explained in the full walkthrough. And honestly, all you're doing is creating a structure of values that you want to fill in. What do I want to estimate? And it's like, okay, I want to estimate oak on beech. There it is. Takes a little bit of getting used to. Ultimately, once you are used to it, it's not that complicated. And then this is just feeding the model argument. So all the matrices we just set up get fed into the model. And that's what runs the model. I've saved out the data because it takes a minute or so for the model to run. So I just saved the output. It doesn't take a very long time to run, but too long to do live. So in this case, I'm fitting the model twice. I'm fitting it with no interactions, and I'm fitting it with these pairwise interactions between oak and beech. And the ultimate output for each of those, if we check out the coefficients, we can run coef on the models, 1 and 2. And here are our coefficient estimates. The intercept for each species, the effect of each well, these are the autoregressive processes alone, other on other, hardwood on hardwood. So this is a diagonal of that C matrix. Our B matrix, which is the effect of charcoal accumulation rates on each species. So charcoal accumulation on hardwood, a very slight negative effect, a bit more of a negative effect on elm and beech. And in our second model with interactions, we have these additions. We have 2 extra rows here. We have the effect of oak on beech and beech on oak. And we have a bit of a negative effect of beech on oak and a very close to 0 positive effect of oak on beech. So that's the process, well, very whistle-stop tour of the process of fitting the model in code. The last thing to say about this is the p-values that are estimated in the coefficient output are likely to be a little bit inflated. And this is what we found out through our simulations. So we usually don't use these coefficient estimate p-values directly, and we run a bootstrap on the model. And so there is a facility to do that. You take the model object, for example, I've named mine MNTS mod int4 with interactions, and I can run the code boot for bootstrap with that model and say give it 1,000 bootstraps. But that will, of course, take quite a few hours to run. But we found that you pretty much should bootstrap your estimates if you want to get more reasonable p-values and reduce the sort of type 2 error. Um, and that's all for the coding. I hope that wasn't too condensed, but I did my best. And we have a couple of minutes remaining for any more questions around that.
That was great. Thanks, Quinn. And yeah, it's really hard to show how to do all the coding stuff quickly. So I think you did a pretty good job given the time constraints. Does anyone have any questions? And feel free to unmute yourself and just shout out questions or type them in the box if you have one. I've got a quick one whilst we're waiting. Like, what's next for this? Like, where are you planning on kind of expanding this to, or are you moving on to something completely different?
What's next? There's a couple of facilities I'm hoping to include. For example, honestly, some just user-friendly things like being having species names printed out right there. I'm used to it because I programmed the whole thing, so it doesn't take me much thought to do it. But I realize a new user, it would help to have some visual aids there. Also include some helper functions for analyzing your the sparsity of data in your model. Possibly do something, improve our AIC outputs. Right now, I didn't demonstrate the AIC. It is printed from the model, but Tony more specifically found it not to be too reliable in this context, so requires a little bit of adjustment before you rely on AIC for like model ranking. So maybe we'll look into like bootstrapping AIC. We'll see. There's a lot of places this can go, include a Kalman smoother, as well as a Kalman filter on the back end. Um, so there's much room for expansion as always. It's just a matter of time.
As always.
As always. Time and funding, what we always need in academia.
Yep. Any questions for anybody? Anybody typing a question and just needs a little extra second? Just give us a shout. Okay, I think you might be off the hook. So
Great.
thanks again to Quinn. That was excellent and I think a really exciting package and also really lovely help materials as well. So that's always great to see. Like I said, if you are publishing a paper with us or you have published paper with us and you want to do one of these in the future, do just let us know. But otherwise, thank you for coming along to this one and hopefully we'll see you at another one at some point in the future. Thanks.
Thanks everyone for attending.